like you're telling me evolution can't be true because there are too many non-functional permutations of a protein?
Yeah, I mean, if there's so I mean, like, if there's 20 amino acids, so the total number of possible sequences is like 20 to 150, right?
Well,
So,
if the protein has 150 amino acids, then yeah.
right, but evolution has to like search this space by like incremental steps or like mutations. So, I mean,
No.
natural selection can only preserve what already works. It can't.
Yeah,
It can't plan ahead.
that's true, and that's not a problem.
So, well, the argument with it will say it can't plan ahead, though, right?
Yeah, I know.
So, if it can't plan ahead, what would your argument be to that?
Why would it? So why would it need to be able to plan ahead?
I mean, not because natural selection basically only selects traits that give a current like survival or reproductive advantage. I mean, it has no ability to plan ahead or build like multi-step structures. I mean,
Yes,
uh,
but there
unless every
are.
intermediate step is also beneficial. I mean, this makes
Yeah,
it
an
inherently.
intermediate step can absolutely be beneficial.
But I mean, it would force evolution to explain every step, not just the end result.
Yeah, I know. It can explain the intermediate steps because the intermediate steps can be beneficial. So, for example, take you know what leaf mimicking insects are?
Yeah.
So, when you see a leaf mimicking insect, it's really insane because some of them they even have the brown spots on them. They have little
Uh-huh.
pieces of their body where it looks like part of the leaf has like decayed or come like not fallen off, but like they're not perfectly shaped, right? They're very convincing leaf mimics, right? And so the idea is evolution has to be able to see that with foresight and progress toward that goal. But uh, but it doesn't because let's imagine um
Hmm.
so there are no leaf mimicking insects, but there are insects, right? And let's say that an insect lives on a tree. You with me so far?
Hmm.
Okay, and that insect, um, let's say the insects give birth to absurd numbers of offspring, right? So let's say an insect gives birth to, I'm just going to say 100 offspring. Some of them are a shade of green that's really close to the shade of the leaves of the tree they live on, and others are not. So some of them blend in with the environment better. So the ones that blend in with the environment better have a better statistical chance of surviving and reproducing, and their offspring are going to look more like them, not more like their siblings that don't blend in as well. Does that make sense so far?
It makes it. It does make sense so far. Yes.
Okay. So this insect does not have all of the hyper specific leaf mimicking phenotypic traits yet, but it has part of it, right? And the key is the full leaf mimicking insects don't exist yet. But we can, natural selection can incrementally pick out. I'm saying that it does it consciously or something, which isn't the case. That's just the way we talk about things. But now that the shade of green has been picked out, now an insect that's very slightly flatter than another looks even more like a leaf, and that kind of variation can occur in a population. And so they gradually, this kind of, we call it directional selection, pushes the population, that species or whatever, to become more and more and more phenotypically specialized. But it can happen. The key thing here is it can happen in tons of different ways because there are leaf mimicking insects, there are stick mimicking insects. So it could be the case that in that original population, some of them are born brown. Well, now they're going to live on the branches and blend in better. And once that gets started, then bodies that are ever more slightly elongated or insects that have a proclivity to stand still more often are going to be hidden better. And then that just keeps getting more and more exaggerated over the generations.
Okay. No, I do hear what you're saying. I mean, yeah, if I can grant to you to an extent that when it comes to leaf mimicking insects, that this could be the case. The issue here would be is that if you're saying gradualism works in this case, the problem is that partial mimicry isn't really good enough. So
Yes, it is.
natural selection would not favor it because it may actually
Yes,
even
it would.
penalize it.
No,
It would penalize it.
no, it wouldn't penalize it. You're comparing partial mimicry to
Mhm.
complete mimicry. The complete mimics don't exist yet. They're not competing against complete mimics. They're competing against the other members of their species, and the species is moving toward more perfect mimicry, but isn't there yet. So the less than perfect mimics absolutely have a survival advantage over the other even less than perfect mimics. Perfect mimics don't exist yet.
Okay, so if I grant you that with leaf mimicking insects, this to be the case, um, the question I'd have for you next would pretty much be that like, are we to believe that these random mutations in selection, basically with no planning, produce this level of precision, step by step, but basically, I mean, the odds of this happening without coordinated guidance is vanishingly small. I mean, that's the problem. Is that like, yeah, I can grant you like with leaf mimicking insects, maybe the case. The problem is that you're saying that with no planning, random mutations produce this level of precision across the board. Because you see it not just in insects, correct?
You see it in everything, but we already walked through the logic of it. Every population is going to have some variation. That variation is not planned ahead, but those phenotypic variations that can produce a statistically better chance of survival are absolutely capable of being selected in the environment, and then that changes the genetic composition of the population because certain individuals with certain trait expressions statistically survive more often, and then therefore their offspring make up more of the population every generation, and that's what drives the like phenotypic diversity and well really it drives speciation. So
Yeah, I mean, but like mimicry, like I would say like mimicry involves like multiple traits, governed by multiple systems. I mean, like, the thing is like, where's the genetic mechanism that makes this happen? I mean, there's no known like leaf mimic gene, right? So if mimicry involves
well
multiple
there
traits
are
governed by multiple systems, I mean,
very few traits have a gene for them. Like human height is like it's literally thousands of genes work. Well, maybe not thousands, but certainly hundreds of genes that work together. So there's no gene for human height, but there still are clearly the difference. But the environmental effects of human height are extremely subtle. Now we don't have the gene for human height, but it's very clearly overwhelmingly genetic still.
right. I mean, I'm trying to think of how to respond. Kind of. I do hear what you're saying. It kind of comes down to. I'm sure you've heard this 1,000 times. I mean, this is like a very common fun run thing. But I mean, like in theory, I mean, like the the likelihood of this happening is the same as like a hurricane producing a house. But it's like
Yeah, it's those.
in theory, sure, but it's like statistically absurd in practice.
That's because those explanations are always a really terrible straw man of what's actually happening, because those examples, what they do is take a current living organism. Well, I mean, the biggest problem is that it assumes that the process is a random, unguided. Well, I don't want to say unguided, but it assumes it's a random process, and it's not. What accounts for the variation is random, but the selection is very non-random. We're going to pause for just a second because I want to show everybody this. This is from the YouTube channel Stated Casually. He does evolution educational videos. But here's that leaf mimicry played out in front of us. The idea of, so those guys are not selected for because they don't blend in. The green one blends in. It doesn't look like a leaf yet, but every generation, slightly different. That went a lot faster than I thought it would. But every generation, slightly different variations in the population pop up. And then that's how we can get sort of each step in the phenotypic variation over and over again. So I slowed it down. So it's like half of what it was. So there's the idea of how it works right there. So anyways, I just wanted to show that because it's cool.